So our second speaker is David Lane, and he is going to be building on several of those aspects through the commercialization of robotics, and particularly the artificial intelligence. David is a professor and co-founder of the director of the Edinburgh Centre for Robotics. He has a long experience in robotics, particularly from the work he did founding CBite in 2001, which he led until 2010, and developed a lot of the commercial applications of the artificial intelligence which are used in many groundbreaking commercial AUV vehicles. And more recently, he's been heavily involved developing that with the foundation of the Edinburgh Centre for Robotics. He's been very influential in getting national and international funding for robotics through the work of the UK's National Robotics and Autonomous Systems. Through the strategy there, he's got multi-million-dollar, hundreds of millions of dollars of investment. He's also very influential in Europe in getting European investment in robotics. And I would say he's been one of the leaders in this area. He has many awards, but particularly he's been elected to fellowships of the Royal Academy of Engineering, the Royal Society of Edinburgh, the Society of Underwater Technology, the Institution of Engineering and Technology, and the Royal Geographical Society. He was appointed CBE in the Queen's New Year's Honours List this year for his contribution to engineering. David.
Thank you, David. It's great to be here. This is a bucket list moment for me. I'm told Blaise Pascal, addressing the Royal Institution a long time ago, said, "Ladies and gentlemen, I will be brief." Had I spent more time preparing, I would be briefer. And one of the things I've always wanted to do is stand here and say that in front of an audience. So thank you very much to the organizers for giving me that opportunity. And I'm going to click this and see if it works. Right, before we get into the subject of my presentation today, I'm going to give a quick plug for the Edinburgh Centre for Robotics. Dave was kind enough to introduce it. It's a joint venture between Heriot-Watt and Edinburgh University. It's really an engine to try and get lots of PhD students through in robotics generally, not just marine robotics. We've got about 100 or so that are going to go through in the current funding and the current program. There's a load of different PIs from across engineering and informatics in both places. And the key thing we're trying to do is produce kids who are innovation ready. So we want them to be able to be aware about how innovation happens and in some cases go and start the businesses. So we have the means to do that. So it's a very exciting adventure from our point of view. And one of the bits of funding we're most proud of is £6 million worth of investment in a thing called Roboterium. We're building new buildings and we're opening new facilities. And there's a fair amount of investment in marine gear there, so you'll see some AUVs and surface vehicles and so on, but also in other kinds of robotic equipment, humanoids. And you'll find a lot of the leading edge, as you'll see shortly as we go on, AI work is happening not only in the ocean, but also in humanoid research. And we've got teams working on that, so it's quite exciting. And I've gone backwards. Right, now I know what I'm doing. Right, so the title I chose was Artificial Intelligence in Marine Robotics, What's Hot and So What? And in 20 minutes or whatever I've got, I'm going to try and do a bit of a tour of certainly what's happening in marine robotics, and try and link that to the so what. There's a little bit on societal implication that I think is quite important, so I'm going to try and cover off some of that at the end. And typically when I do these things, I tend to talk about the two approaches. There's an AI approach to getting intelligence, and there's also a biomimetic approach, and there's one or two people here I recognize who are into that kind of thing. I'm not going to say so much about the biomimetic thing, although I will say a little bit at the end about some of the ways we're using it for sensor technology in the lab. Let me start with this. Jim Jamieson's here, so plug for them.
The deepwater line of business is one of Shell's most important investment priorities. With decades of experience in deepwater, we continue to drive an innovation agenda focused on safe and robust operation so that we can responsibly unlock energy resources for future generations. Globally, we operate a large number of subsea facilities, and the surveillance and integrity of that infrastructure is extremely critical, and it must be a part of our innovation agenda. Subsea inspection is a key aspect to verifying the integrity of those facilities and that infrastructure that rests on the seabed. Common approaches for subsea inspections utilize either divers or remotely operated vehicles, ROVs. These vehicles are controlled by human operators from a surface vessel. As our infrastructure expands globally, we will be using more ROVs in our operations and more divers, resulting in higher inspection costs and higher HSE risk. We believe there is a simpler approach that will allow us to dramatically reduce costs and lessen the HSE risk. With artificial intelligence and advances in autonomous underwater vehicles, Shell has developed new and innovative solutions to deliver subsea inspections.
Through collaboration, we can maximize leveraging the expertise and capabilities of our vendors, and together we can deploy the technology faster and quicker so we can make business impact to our global assets.
The autonomous inspection vehicle, developed by Subsea 7, is a highly maneuverable underwater vehicle that is able to perform an autonomous subsea inspection, alleviating the necessity of support vessels. Subsea 7's autonomous inspection vehicle is marketed as having several advantages over the torpedo-shaped autonomous vehicles, such as enhanced ability to stop, hover and move close to the structures, improved real-time decision-making using artificial intelligence, and there is no need for surface vessels to aid navigation. Over the last 2 years, Shell has been working with Subsea 7 to extend its capabilities and complete a commercial qualification program. As part of it, we recently conducted a sea trial at one of Shell's offshore assets. The purpose was to test various technical aspects of the autonomous inspection vehicle in real-life situation. In a first for the industry, we'll be using an autonomous vehicle to accomplish a riser inspection on a live asset, as well as an inspection of the subsea structures. The significance of this trial is to enable seabed-to-surface inspections of risers, mooring lines, and tendons.
Specifically on the inspection, it focused on visual inspection and some close visual inspection. And I was particularly keen to say, can we really get up close and personal to some of this live asset? The AIV technology that we've jointly developed in collaboration with Subsea 7 has a couple of distinct advantages over the existing methods of operation. It is deployed on the seabed, it can launch from the seabed, gather the information, run its missions, come back, we can download that data, we can then process that information, and we do that with less exposure to the individuals on those vessels in that offshore world. That is of fundamental importance for us because it reduces the HSE exposure.
With this innovation approach, we have greatly expanded the available set of inspection capabilities, allowing for a more comprehensive set of results at lower cost and lower risk with a higher rate of inspections. The autonomous inspection vehicle will allow us to boost asset integrity for our underwater facilities.
One of the ways you know you've made it in life is when people don't mention you anymore. And that was an excellent video promoting Shell, and it was made by Shell, of course, and mentioned Subsea 7. No mention of Seabite, certainly no mention of the Ocean Systems Lab Heriot-Watt. I don't care. It's a gift, right? And you kind of feel good that that's out there and it's happening. I think the key point about that video for me, apart from the nice pictures of the vehicle swimming around, and Jim Jameson from Subsea 7, he had a big part in that program, is the fact that they don't really talk about the vehicle so much as the reason why, which is about asset integrity management. So when we have these vehicles, it's not, and the AI inside them, it's not just about what the vehicle can do, it's how it fits into a system, and I'll come back to that point later on. So moving on from that, that's a state-of-the-art system. It has some AI inside it. Tom said that in the video. It's script switching, so it's fairly basic AI, but it's reliable AI. And what the sort of things we're working on at the moment, which is where the future's going, are developing onwards from that, and that's what I want to talk about today. So we think about the notion of persistent autonomy, and this is the sort of thing that we're reaching for in the next generations of these kind of vehicles and the systems they sit in, where essentially they have to work with limited resources and access to a human operator for extended lengths of time in environments that are unfamiliar. And that's a big ask for this kind of autonomy. So I'm going to run through a few things that we've been doing leading up to that kind of persistent autonomy, primarily from a program called Pandora, which is just finished, which is an EU program with a load of people you see on the slide here from around Europe. One of the things that's really important is control. So we spent quite a lot of time investigating how to get vehicles to stabilize in currents and in waves. I think if the next one's going to, can we get the next one? It's not going to go, doesn't matter. And the key AI point about this, here we are trying to hover the vehicle in unusual attitudes. The AI point inside this, for those of you who are technically minded, is that the control systems we're working on are using AI systems in order to model the nonlinear dynamics of the vehicle. So part of doing a good control system is if you have a good model of the vehicle, then you can make it model reference. There's a number of schemes you can use. And we've been working quite a lot with a scheme called LWPR, linear weighted projection regression, which basically does a series of linear fits of the vehicle nonlinear dynamics. And that works really well, but it has a training phase associated with it, so you have to have access to the vehicle and put it in the water. So machine learning and artificial intelligence are impacting right down at the lowest level of the hierarchy for working on the vehicle. Some other examples of things we've been doing using AI in Pandora. This is one called skill learning. So you'll see the movie that's running at the moment. This chap is teleoperating. It's a vehicle from our partners in Girona. It's a Girona 500. It's got a manipulator on it, and what we're going to try and do is turn a valve. It's an autonomous vehicle, even though it's got a cable on it for these experiments. And what he's doing is doing 3 or 4 runs where he's teaching the vehicle how to do the task. So the vehicle is learning the task. But it's not just like in a manufacturing environment where what you're learning is a series of control inputs to the, in this case, thrusters or robot arm, it's the joints. Right? What it's doing is learning a lot of different probabilities. It's a Markov process that's in there. And so what that means is after 3 or 4 iterations, the vehicle's learnt enough that when you put it in to try and do the task on its own, it can replay the task, but it can be persistent in the sense that it can deal with uncertainties, it can deal with disturbances. And if we let this video run long enough, you'd see a propeller coming on and the current, and it offsets the current and so on. So that's a very important part of the persistent autonomy piece, part of being able to not only record and store a behavior, because if you're going to have autonomy, how do you teach the vehicle what the behaviors are, but then being able to have a behavior that's robust in the presence of noise and disturbance. And in fact, if we could run the other movies as well, here's some other examples of tasks we've got it to do. It's doing a chain cleaning operation here, top right. So it's not a real chain, by the way. It's too heavy. It's a pretend one. So I think the chain might move, which you wouldn't normally get in practice. But it's the same thing. Reaction forces on the vehicle, disturbances all around, and it still manages to stay there and do it. And indeed, what you're seeing in the bottom 3 movies are, if you get a thruster failure, it can deal with that. And so although the vehicle might not be able to hold a heading, when it moves, it can at least move safely to the right position in space, and so not cause any damage. So these are very powerful techniques, and we're quite proud of having developed these, which are very heavily dependent on artificial intelligence. At the heart of a lot of what we're doing in there, and the next phases of work, are borrowing from computer scientists who deal with what's called the Semantic Web. And it's the thing that Tim Berners-Lee went on to do after he'd founded the World Wide Web. And thinking about how can we have semantic content and store it and transmit it. And at the heart of the planning operations that we want vehicles to do when they're operating on their own are different forms of what are called probabilistic graphical models, or ontologies in this case, which are semantic sets of relationships that describe the vehicle, the world around it, and the probabilities that you're right in the linkages between your beliefs there. And certainly we've done quite a lot of work with that in the same program in Pandora, trying to do things like, in this case, we're up at Fort William, at the Underwater Center. We're doing some inspection around the pier legs, and on the right what you can see is the sonar scans from the vehicle. It's got a forward-looking blue view sonar on the vehicle, and it's learning how to inspect the pier legs without actually having an a priori model of where the pier legs are. So it sets off, it explores, it finds the pier legs, and it adapts on the fly the task it's trying to do as it discovers. And that involves using simultaneous localization and mapping, or SLAM. It involves ontologies, because it has to have a store of, well, what objects are there in the world and where are they. And there's a lot of planning and mission replanning on the fly that goes on, where having detected new objects, the vehicle has to then replan where it's going to go in order to do that. So again, a successful set of experiments, and something that we hope we can transition in the future, because not all objects that you're going to inspect do you know about where they are. And indeed, we've been looking at ways of developing that into situations where we've got multiple vehicles. So here you've got an example. It's not underwater. It's in the lab where we're running a turtlebot, a ground robot, and an aerial drone. And what's happening is the turtlebot's moving in to try and do an inspection. In this case, there's a series of obstacles in the way. It can't see well enough which way it has to go in order to progress. So what the aerial vehicle does is fly over the top, map it, and then communicate, produce some ontologies about what's there, map it, and then communicate back to the turtlebot in order to tell it which way to go. So the vehicle can decide which way to go. And that's a step forward from the sorts of commercial collaborative software that are around at the moment. And again, it's using this high-level planning and semantics as part of the activity. I'm going to show this one because this is starting to take us towards where how does this link to asset integrity. This is actually a live demo taken from a conference actually called Automatica, and it's some colleagues, a guy called Michael Beetz, who at that time was at the Technical University of Munich, and it's a PR2, it's a humanoid. The thing it's trying to do here is make popcorn. And I'm showing this because in order to figure out how to make popcorn, cook popcorn, it downloaded from WikiHow the recipe for how to do that. So it's using and relying on shared knowledge services in order to do that. It doesn't know how to make popcorn. What it does know is to go where to go and find it. And having open architectures that allow us to share the information, share the planning information about how to do the task is important. This is cheating. The protein-based robot is doing rather better than the mechanical one. The point here is that even though it downloads the recipe how to do it, that's not enough to actually carry out the task. There's a lot of other planning it has to do in real-world environments to figure out, well, first of all, I have to put the pot, I have to light the stove, I have to open the drawer to get the pot out, and the sequencing the operations. So even though it's got a plan, there's a lot of further planning it has to do on the fly in order to carry out the task. And this shared knowledge service approach, I think, is the thing that's going to be at the future of a lot of robotics in general, but particularly in the ocean, because some of the things you want to inspect are going to be perhaps not as complicated as making. This is good. Go on, do it. There we go. Right. Okay, that's harder than you think, right? It's easy for us, but it's hard for him. Anyway, enough humor. Right. And so, you know, in our world, you know, we represent the world using ontologies. We represent the assets that we're trying to do integrity management on. And these sort of semantic representations are then the things that are used to brief the vehicle what to do. So when you come to do asset integrity management for your field, you have the means in the semantic information that not only allows you to do that integrity management, to look at where failures are occurring, to predict in condition monitoring when failures are going to occur, but also to do something about it and vector the vehicle in there. So in our brave new world in the future, we expect more sophisticated systems where effectively we're joining the big data of the asset with I'll use the intelligence word of the vehicle and its autonomy in order to carry out the task. So we say robots become the arms and legs and sensors of big data in that sense. Coming back to my themes of AI and biomimesis, I want to say a little bit about the biomimetics side. Certainly animals are great at doing all these sorts of things that we want to do. The tasks that, the navigation tasks that turtles can achieve, the things that hydrodynamically seals can sense with their whiskers are just phenomenal. And so we've certainly got a couple of programs going in the Ocean Systems Lab, Heriot-Watt, and a Centre for Robotics, looking at how do we develop on that. And the one we're very excited about at the moment called Lakshmi, it's an EU program, it's got a bunch of different partners in it. You can see the logos there, led from Tallinn University of Technology, but also Hydro Group from Aberdeen, cable company. What we want to do is copy what a fish does for sensing hydrodynamically what's around it. Fish has a sensor called a lateral line. It detects flow, and using that, the fish can hydrodynamically image the environment around it. So it knows basically if there's predators coming to eat it, it knows where the other fish are, it can swim in formation, all that kind of thing. And so that's a very valuable thing to be able to do, and we're certainly up to speed now on a system that uses a different technology to the lateral line technology, but the same principles, in order to build cables that we can lay on the seabed that can do hydrodynamic imaging. And that has a number of different applications, from renewable energy. You can monitor the vortices coming off your turbine, through to looking for the bad guys if they're coming into your harbor, and environmental monitoring if you want to monitor mixing processes in the ocean, for example. So very early stages with that technology now, completely bio-inspired from the fish, and very exciting if we can get it right. And of course, those of you who know us of old, Hydroson is a spin-out company from our latest spin-out company from the Oceans Lab. It's doing wideband, wide-beam biosonar modeled on how the dolphin works, and we've had some very interesting results recently working on some archaeological sites up in Tallinn, where we've been doing some incoherent SAS processing on the data from the wideband wide-beam sonar. It's a multi-chirp wide-beam signal that the dolphin uses. We've been modeling that, and it turns out that's very good for detecting man-made objects, aspects of man-made objects. We can, and at quite low frequencies as well. So again, not time to talk about that here too much, but an example of how we're using bio-inspired technology. Right, this is a movie, back out of the ocean now. This is me getting into my ethical mode to finish off for the day. This is the latest video. You may have heard of a company called Boston Dynamics. They're based in Boston, as you can imagine. They used to be an independent company. They got bought by Google 18 months ago, 2 years ago. And this is the result of some of the investment that Google have made. There's a video that came out last week or the week before, I think. And it just shows that really is the state of the art with where humanoid research is going. To me, this is the most marvelous example of control. There are large numbers of degrees of freedom. It's dealing with disturbances, as you can see. And if we could just make it go a bit faster, we'll get to the bit I want to get to. It's actually the result of quite a lot of investment that Google have made. It's all been done rather secretively. It does consume enormous amounts of power. Now, this is the bit I wanted to get to. This is whole body compliant manipulation. So the whole of the robot's body is moving in order to do the carrying operation, it's exhibiting not only position control but also force and torque control as well. So there's compliant motion going on there, and this is the bit I want to get to. So he's picking this up here, and you're going to see this chap coming in from the left, right? So this, to me, is a great example of how fantastic the control system engineering is using AI principles on this robot. When this came out on social media, right, you know, the response of the public took me by surprise, but then it didn't take me by surprise, because the basic response from everybody was, "Why are you being so cruel to your robot?" Right? Yeah, it's not fair. Robots have rights, right? You know, and there was a long chain of tweets. You could go on, you know. Yeah. And the point being, how people perceive robots is actually, most of us here, I guess, technical, so we see the technical excellence that goes on there. But most people don't, right? Most people, they're used to seeing the movies, they're used to seeing Star Wars or whatever, right? And so their response is a much more emotional response. And I think that has created, to some extent, a fear around robotics and about this is the so what bit of my presentation, a fear about robotics, about what the implications are going to be, and not just about, you know, being cruel to robots, but also about, will a robot take my job? And I've certainly been on TV a few times recently trying to answer that question to journalists and others. So there's a few things I like to try and say about that, it really as closing comments really, about that. And people say, well, you know, if a robot takes my job, there's a hollowing out in the economy going on, you know, what will happen to unemployment? So I took the trouble to go back and look over the last 100 years at the evidence about what happened to UK GDP and also our employment. And what you basically see over the last 100 years is whereas employment has increased by 50%, GDP has increased by 500%. So every other technological revolution we've had, computing, cars, have resulted in increases in productivity rather than increases in employment. And indeed, if you look at the graphs of, this is trying to plot time against the the growth of the retail price index and unemployment, what you see largely is that financial events are the things that correlate with the markets, are the things that correlate with unemployment, not the rise of technology. So although people's jobs and earnings go up, of course, because we all get richer and we'll get more productive, and, this is the one, rising tide floats all boats. I mean, it is true that here's an example that shows how profits have gone up and wages as a percentage of GDP have gone down. Of course, profits are going to go up because you're more productive, and therefore, naturally, you'd expect wages as a percentage of GDP to go down because your GDP goes up, right? So, and I think the worry people have is that, well, doesn't it mean that, you know, the wealth gets concentrated in with only a few people and the rest of us are poor? And actually, I don't think that's the case. I think the wealth is not there are pockets of extreme wealth, but if I look at how some of even the poorest people live today, maybe not poorest people in the third world, but certainly poor people in our country, they live better than some of the richest people of 100 years ago. Right? They have access to information, they have access to healthcare, they have access to travel, EasyJet's full of people traveling. So it's not just about what you earn, it's also about the services that are enabled by the technology as it comes, and that linked to productivity. So I'm not worried about the rise of robots. I think robots are going to be something that's important for us to engage with. And I like to include, those of you who are of a certain age might remember Charlie Chaplin. This is a sequence from Modern Times. You know, would you rather be doing a dull, mundane job like this and earning not very much, right? Or would you rather be doing something that's more supervisory in nature? You know, with the rise of Baxter, the nature of factory automation is going to change. So you have time to go and do other things, right? Rather than what poor Charlie's having to do here, right? So there we go. So I'm going to finish with an epilogue, the last words. And here's Bill, looking much younger than he is now. We always overestimate the change that will occur in the next 2 years and underestimate the change that will happen in the next 10. Some of these AI methods are coming to fruition now. We're seeing them in the ocean in things like AIV. There's a lot more to come. People want it to happen faster and faster. And if it hasn't happened by next year, they lose interest. Politicians can be like that. Not all of them. But then suddenly one day you wake up and it's all changed and it's happened around you. And certainly what is happening around the world at the moment is that nations, the US, Korea, China, I was there recently, are running hard at robotics as an area, and we in the UK, we have a great platform here in the UK. We have fantastic centres, Edinburgh Centre for Robotics, of course, but Oxford, Bristol, Southampton are other excellent places, which is the base of the innovation pipeline, and we have we're developing quite a good innovation culture, and there are even 3 Chinese venture capital companies set up in London now, ready and prepared to invest. So I think the future's rich. We just have to press the button and go and make the most of it. Thank you very much.
Thank you, Dave, for a very stimulating talk there. We are running a little bit behind time, but I would like to offer the opportunity of a couple of quick questions for either David or for Gwyn. Any quick questions between now and your coffee break? Anyone going to be bold enough? Okay. If you could give your name and affiliation.
My name is Nick Lambert. I'm an independent consultant doing a lot of work for the Satellite Applications Catapult. Gwyn, I'd like to congratulate both speakers on 2 brilliant presentations. You talked about the rise of the robots. You touched on some of the work that they do. Has anybody done any work into the exponential increase, if it has been, in data gathered in places that we wouldn't otherwise know about? So what have we found out from using autonomous vessels?
I mean, that's an entire conference, Nick, let alone an answer.
Has it resulted in a major increase in knowledge? Do we know?
You saw the rise in the number of Argo-related papers. The knowledge of the deep ocean from that single Argo program really has transcended what we knew before. Not just scientifically, but the ability to feed into the operational environment. The work under ice has radically changed people's views of the fate of the West Antarctic ice sheet and the importance of knowing that for future sea level rise, because that is the biggest uncertainty in the future sea level rise projection is the fate of the ice sheets. Two quick examples.
Yeah, very good examples. Another quick question? One more. Sorry, up there.
Yes, two very nice presentations. David, you talk about training the robots. What's the relative cost of, sorry, it's just the Merrick Strockos National Oceanography Centre, what's the relative cost of the training time via the actual experience of using them? How much training do you actually have to put in to make it do what you want?
That depends on what you're trying to do, of course. With the skill learning stuff I showed about learning how to turn a valve and that, you could run it 3 or 4 times, and that was enough for it to learn. Some of the other things, machine learning in general, actually, it needs a lot of the deep learning work. We've got these neural networks, but with lots and lots of layers, hierarchically arranged. That needs lots and lots of training data, and actually that can make it prohibitively difficult for many applications. So big data is not applicable to everything. The large corporations, Google and everybody, they have access to lots of data, so they can do that. It's not so easy for us in the ocean. And of course, as you're hinting, it's expensive also if you're at sea doing things, to get time on and stuff, So that's why we try and use simulation a lot, good quality simulations, and do it in the test tank as well.
Okay. Any last quick question? Okay. Dougal.
Thanks. I'm Dougal Goodman from the Foundation for Science and Technology. Thanks for 2 brilliant presentations. Question for Gwyn. Would we have accelerated the development if we had more money, or was there a constraint on the skill level of the people in the program?
On the skill level?
The number of skilled people that you were able to...
People. Possibly, but managing the interaction amongst a large number of skilled people is a challenge in itself. Many of I showed all of those faces at the start. So there was not just one's own team doing the innovation, but the supply chain out there in industry, working on things like fiber optic gyro compasses, were absolutely essential. So in fact, there was that global distributed team in suppliers that was absolutely essential. But the 2 years with AutoSAR, I don't think you could have shortened that effectively.
Tremendously short period.
Yeah.
Okay. I think we'll have to draw it to a close now. I'd like to ask you all to, again, give thanks to our 2 opening excellent speakers.